Hello everyone. In this video I'm going to go over part 2 of practice test 4, which is the take-home Excel part of the test. So we'll start here in the first tab, which is t-test 1. So let's read the stuff in the text box here. So this data is taken from U.S. colleges and universities that primarily grant bachelor's degrees. It was retrieved from the U.S. Department of Education College Scorecard website during fall 2022. The cost of on-campus room and board are shown for each college, with a random sample of 100 public colleges in column A and a random sample of 100 private nonprofit colleges in column B. Is there enough evidence to conclude that the mean cost of on-campus room and board is different for public colleges and private nonprofit colleges? To answer the question, complete the two-mean t-test procedure and put your answers to the questions in the yellow cells. So I put the procedure table in here for you guys, and you're going to go through this procedure, and then up here is where you're going to put the answers to things that you do during the procedure. Okay, so first question up here is, are the assumptions of the test met? Explain why or why not. And so we're looking at the assumptions down here in the procedure table. So the first one is random samples. So let's see here. It does say random sample and random sample. So I'm going to start off my answer here with yes, we have random samples. And then the second assumption is about sample size, distribution, and outliers. So we have sample size 30 and up because they're both 100. And then it says any distribution is okay as long as there are no extreme outliers. So we need to check for outliers. So I'm going to select columns A and B by clicking and dragging from A over to B. Then I'm going to go to the Insert tab and put in a box plot. Okay, so I'm only seeing one outlier on here. I'm just going to move this over here where I can look at it separately. Okay, so I'm going to put the legend on here. All right, so I'm seeing one outlier on the public colleges, but it's not very far from the rest of the box plot, so I would not call that extreme. Okay, so we do have random samples, and there are no extreme outliers with 30 plus sample size. Okay, so we are good to go there. What is the alternative hypothesis? You can use words or symbols. So I think the easiest way to get the alternative hypothesis is literally just copy it from the question. So is there enough evidence to conclude that whatever comes after that is the alternative hypothesis? The mean cost of on-campus room and board is different for public colleges and private nonprofit colleges. Boop. See, just paste. Okay, and then I guess I'll capitalize it. All right, so that does put us in, because the word being used is different, rather than less or more, that does put us in the two-tailed test situation, this green column here, where the alternative hypothesis is that the two means for the two samples, or for the two populations, are not the same. Okay, so we are going to be using the 2 when we go to do the p-value formula. We're going to put 2 for the number of tails. Okay, next question, do the sample means match the alternative hypothesis? So do the sample means satisfy whatever the alternative hypothesis says, that the mean cost of on-campus room and board is different for public and private nonprofit colleges? So if we look at the two means here, if you hover right over the X on the box plot, you can get the exact value. 11,630, and this one is 11,146. So they are indeed different. So yes, the sample means are different. Okay, now for the null hypothesis, using words or symbols. So I'm just going to copy, paste, and I'm going to change the word different to the same. Or you could use the word equal, that's fine too. Okay, so you just make the opposite of whatever the alternative hypothesis was. 3 population types, which is this 1, 2, or 3. So that is given in the table down here. So 1 is for paired data, meaning your data is 2 different variables from one sample. So we do have 2 different samples, so it's not that. 2 is for when the 2 populations have the same standard deviation. We haven't been told anything about that. 3 is for when the 2 populations have different standard deviations, or for when you're not sure. So we are going to do 3. And we've always done 3 in this class. We've never done anything else. I'm just gonna align that on the left so it shows up a little better. Okay, there we go. Calculate the p-value. Okay, so the formula is t.test, and then there are 4 arguments. So array 1, that is the first sample. So I'm just gonna scroll over here and click on the A to do A:A, which is just everything in column A, right? And then comma, and then I'm gonna click on column B, or you can type in B:B. All right, so that's for the second sample, comma, number of tails. So we are doing a 2-tailed test because the hypothesis, the alternative hypothesis is that the means are different. So that's gonna be 2, comma, and then the type, which we answered on the last question, so that is 3. All right, then close parentheses, hit enter. Okay, so this p-value is pretty big, I would say. If you format it as a percentage, you can see it's 27%. So it is way above 5%, which is kind of the cutoff, the largest cutoff that I would say would make a p-value small. So this is way too big to make a conclusion. Right, so our interpretation here is going to be for when p is not very small with a p-value of, and then I'll put the p-value. We do not have enough evidence to conclude that, and then I will just paste the alternative hypothesis. Okay, so with a p-value of 0.2737, we do not have enough evidence to conclude that. All right, and I'm just going to come back up here to the alternative hypothesis, copy that down here, and then I'm going to click it into the bar up here to paste it at the end. Boop, boop, fix the capitalization, and I'm done. All right. So it's going over to the side a little bit, but that's okay. All right, so we do not have enough evidence to conclude that the mean cost of on-campus room and board is different for public and private nonprofit colleges. Which kind of makes sense because, like, usually the tuition is only the part that is subsidized by the government, not the room and board part. So yeah, they do actually typically cost around the same amount, and the only thing that would affect it very much is like how fancy the college is or what region of the country it's in. All right, so let's go to the second tab here, t-test 2, and we're going to do this all over again. So this data is taken from the same place. Those 2 sentences are the same. The cost of attendance is shown for a random sample of 40 HBCUs in column A and a random sample of 35 non-HBCUs in column B. So if you guys don't know, HBCU stands for Historically Black College or University. And then the question is there enough evidence to conclude that the mean cost of attendance is lower for HBCUs than for non-HBCUs? Okay, so we're going to start by checking the assumptions of the test. So the 2 assumptions here in the table are random samples and then the sample size stuff. So I do see the word random here and random here. So we do have random samples. All right, and our sample sizes are 35 and 40, so they're in the 30+ category. And any distribution is okay as long as there are no extreme outliers. So to check for outliers, I'm going to select column A and B, insert a box plot, and I do see one small outlier, but that doesn't seem extreme to me. It seems pretty non-extreme, so I think that is fine. Okay, so we do have random samples and there are no extreme outliers with sample sizes 30+. Okay, so we're good to go there. I guess I should sort of clearly say yes or no, right? So I'll start off with a yes here. All right, what is the alternative hypothesis? You can use words or symbols. So again, I'm just gonna copy this from everything after the word that from the question here. And I'm gonna do a paste text only, or match destination formatting, so I keep the yellow background. All right, so the mean cost of attendance is lower for HBCUs than non-HBCUs. So that is going to put us into the one-tailed test type. So that's where one mean is lower than the other. All right, do the sample means match the alternative hypothesis? So now we need to be a little bit careful, and I'm going to check the box plot. So the box plot, the blue here is for HBCUs, and the mean is 27,918. and the orange is for non-HBCUs, and the mean is 48,446. So it looks like HBCUs are way lower, much lower. So that does, in fact, match the alternative hypothesis. So yes, the HBCU sample mean is lower. Okay, now the null hypothesis, I'm just going to copy my alternative hypothesis, and I'm going to swap the words. So instead of lower, it's going to be greater than or equal. Okay, and now 3 population types. So we do have 2 samples, so it is not paired data. We don't know anything about standard deviation, and so we're going to default to number 3 here. All right, now the p-value. Formula is in the table here if you forget it. So it is equals t.test, and then we have 3 arguments. So array 1 is going to be our first sample, column A. I'm going to click on the A, or you can type in A:A. All right, comma, array 2, that is the second sample. So I'm going to click on column B, or you can type in B:B. Comma, tails, that's the number of tails. So I'm going to do 1 for a one-tailed distribution. Comma, and this is your population type that we answered on the last question. So this is type 3. Close parentheses, hit enter. Okay, so as soon as you see standard, or scientific notation, it has to be really, really small, because you can also use scientific notation for really big numbers, but p-values only go up to 1, so it's not possible to get a really big p-value that's in the millions or billions. So indeed, this little e-09 thing here means this is 6.44704 times 10 to the -9. If you want to take it out of scientific notation, you can put it into number format, so home tab, and then the drop-down menu and number format, and then you've got to increase the decimal places using these 2 buttons here until you see the number again. Yeah, so that is really small, really, really small. So for the interpretation statement here, we're definitely going to go with the first option for when p is very small. So with a p-value of whatever, there is, pick an adjective, evidence to conclude that, and then the alternative hypothesis. All right, so I'm going to do it here with a p-value of, and then I'm going to paste, nope, I guess I can't paste. Let me grab this. Oh, I can't grab the number from up here, right? Okay, I guess I will just try to type it in. So how many zeros is that? With a p-value of, nope, it's no good. With a p-value as shown above. That's what I'm going to go with. I would say this is very strong evidence. It's a very strong evidence to conclude that, okay, and now I really am going to paste the alternative hypothesis. Okay, let me get in here. Okay, fix the capital. All right, there we go. So with a p-value as shown above, there is very strong evidence to conclude that the mean cost of attendance is lower for HBCUs than non-HBCUs. Yep, so HBCUs are a lot cheaper than non-HBCUs. Okay, so that is t-tests, and now I'm going to switch to chi-squared tests. So chi-squared test 1 tab. Let's read the text box here. A random sample of 140 U.S. colleges was selected. I use the same data set for this whole practice test. And each college was categorized as its type, public or private, and its locale, city, rural, suburb, or town. The results are shown in the table. Is there sufficient evidence to conclude that the variables type and locale are not independent? So in other words, are like public colleges more commonly in some locales than others, or are private colleges more commonly in some locales than others? So we will find out. And we're going to follow the chi-squared test for independence. I think I put the procedure table over here, and then the questions are here. So first of all, are the assumptions of the test met? There is only one assumption to check, and that's random sample. And so let's see, do we see the word random here? Yes, we have a random sample. So yes, it is a random sample. Okay, alternative hypothesis, there's only one thing that it can be. There's no choices. It's just written right here at the top of the table. The 2 qualitative variables are not independent. So in this case, the variables are type and locale. So type and locale are not independent. So then the null hypothesis is the opposite, that they are independent. Independent. Okay. And now what we need to do is follow the steps in the procedure table here. So we're going to make a copy of the contingency table and label it expected values for independence. So I'm going to copy this whole thing right here. Just put it down here. So this is where I'm going to put the expected values for independence. So what I'm going to do here is fill in this table with what the values would be if the variables were perfectly independent of each other. So giving every row the same proportions as the totals and every column the same proportions as these totals over here. So the formula for doing that, we're going to delete the entries of the expected table except for the totals, and then fill each blank entry of the expected table with row total times column total, divide by table total. Okay, so you can do it with a calculator if you want to, but I'm going to show you how to do it with Excel. So first I delete the blue entries there, so everything except the totals. And then I'm going to fill in one by one these 8 cells. Let me just zoom in a little. So I'm going to start with equals, and then I'm going to go to the column total. I'm just using the arrow keys because I think it's faster. Times, and then I'll arrow over to the row total, and then divide, and then I'm going to arrow over to the table total, and then hit enter. And unfortunately, this formula is not easy to copy and paste because it moves the references, so I just usually type it 8 times using the right, using the arrow keys to get to the entries that I want. Oops, divide by that one, so that one times that one, divide by that one, equals that one times that one, divide by that one. Okay, I'm sure this part of the video is really fascinating. Okay, that one times, oh, it is that one. Yep, divide by that one. And last one, that one times that one, divide by that one. Okay, cool. So here are our entries. And now what we're going to do is use the chi-squared test to kind of check like how different is this from the ones that we had up here. And so that will tell us whether or not we can make a conclusion. All right, so for the p-value, oh no, I have to check something else first, right? Yeah, I have to check if any expected table entry is less than 5. So it's not these original ones, but the expected table over here that we just made. So none of those are less than 5, so we're good to go here. If any are less than 5, then like it says in the procedure over here, you should stop and don't do the test. Okay, so next thing is we're going to calculate the p-value. So formula is equals chi for chi, and then sq for square, and then chi-squared dot test is the one you want. All right, and then we have actual range and expected range for our arguments. So it's important that you select the right table. If you reverse it, it will give you the wrong answer. So for t-test, it doesn't matter, but for chi-squared test, it does matter. Okay, so actual range is the original table, and you're only going to select the inner entries, not including the totals. It's okay if you select some text, Excel will ignore that, but if you select the totals, it will actually be wrong. So just the ones that are not totals. And I highlighted them there in blue to help you. And then comma, and then the expected table, we do the same thing. So just those 8 entries. All right, and then close parentheses, because that's it. Hit enter. Okay, so this p-value is pretty big. It's a lot more than 5%. So our interpretation here is going to be that we were not able to make a conclusion. So with a p-value of whatever it was, we do not have enough evidence to conclude that the alternative hypothesis. Okay, so with a p-value of 0.1909, we do not have enough evidence to conclude that. And then I'm just going to copy the alternative hypothesis. Type and locale are not independent. So they probably are. Independent is what that means. All right, which kind of makes sense. I wouldn't really expect that private colleges are more commonly in towns or something like that. All right, so let's continue to the second chi-squared test. All right, so a random sample of 129 colleges was selected, and each college was categorized as its type, public or private, and its SAT/ACT test policy for admissions. So they either consider the scores, or they recommend that you send your scores, or they require that you send your scores. So considered just means like they don't recommend that you send them, but if you do, they'll consider it. Okay, so the results are shown in the table. Is there sufficient evidence to conclude that the variables test policy and type are not independent? So I actually think just looking at this, you can kind of already see that they probably are not independent, because for required, there's a pretty even split between public and private, but for recommended, it's like overwhelmingly private, and then for considered, it's a lot more in the private category too. So I think it's probably not independent, but let's go ahead and see if the test is going to agree with us or not, because that's what these tests are for. Okay, so we're going to check the assumptions, which are random sample, and I do see the word random right there. So yes, this is a random sample. Okay, alternative hypothesis is always the same for the chi-squared, just the two variables are not independent. So the variables are type and test policy. Not independent. All right, so now we need to do the thing where we copy the table and fill it in. So I'm going to copy this down here. This is expected values for independence. I'm going to delete the inner entries, so not including the totals. And now I'm going to calculate for each of these the row total times the column total, divide by the table total. So equals, go to one of the totals times, go to the other total, divide, go to the table total. So this part is not very interesting. I do think it's faster if you use the arrow keys, but that's just me. It's also a good idea after you get done doing it, if you kind of eyeball it and check if it looks like your numbers are adding up to the right things. So for example, these two numbers should add up to 58. These two numbers should add up to 16. These two numbers should add up to 55. So if you get like really huge numbers here, then something went wrong. Okay, so those look all right to me. Any expected table entry less than 5? No, they are all more than 5. So that's good. And now we calculate the p-value. So equals chi, chi, sq dot test, open parentheses. So for actual range, you are selecting the numbers in the original table that are not totals. So don't include the totals. And then comma, expected range, you're going to select the numbers in the copy table that are not totals. So just those 6 cells. Close parentheses, hit enter. Okay, so this is quite a small p-value. It's as a percentage, it's 0.2%. Okay, so in this case, the conclusion is going to be the first one for when p is very small. So with a p-value of 0.0021, there is, I'd say this is strong evidence to conclude that, and now I'm just going to type the alternative hypothesis. So type and test policy are not independent. Did I forget to ask for the null hypothesis in this sheet? I think I did. I asked for it in the last sheet though, right? Yeah, I did. That's weird. Because I thought I just copied one sheet from the other, but there's a question missing. Oh well. Okay, so there is strong evidence to conclude that type and test policy are not independent. All right, that's it for this sheet. So now the last 2 sheets are linear regression. So linear regression 1, this is still about the college data. So this is the same first 2 sentences here. For each college, the percentage of students who are first generation, meaning their parents didn't complete college, and the average cost of attendance are shown. Okay, so this is actually all of the US colleges for which this data was available, which means there's like, yeah, 1,600 colleges represented here. So it's a really good data set actually. All right, so this column A is percent of first gen students, and then B is average cost of attendance. So question 1 here, make a scatter plot of columns A and B. So you're going to select column A and B together. Just click and drag over from A to B. And then you're going to go to insert, look for the little dots one, and then just click the one that's just all dots. Okay, so that is a wild looking scatter plot. It's because it's got so many colleges, 1,600 of them, is why it's so kind of dense. You can actually change like formats and stuff to make the dots smaller, but it's no big deal. All right, so question 2, add a trend line to the scatter plot and display the equation and the r-squared value on the plot. So you're going to right click directly on these blue points and then do add trend line. Another way to do it if you can't manage to do that for some reason is select the chart and then go up to the chart design tab and then do add chart element and then trend line. Okay, and you can do it from there too. When you do that one, the formatting tab doesn't pop up to like show the r-squared value and stuff, but you can go to more trend line options from there and then it will come up. Okay, so once you have that up, you're going to go down to the bottom and you're going to check display equation and display r-squared. I think on some versions of Excel it might look like switches instead of checkboxes, but they should still be there. Okay, so I usually move that to the top so I can read it better. In fact, I'm going to put it over here so I can look at the text box and the equation at the same time. Okay, so I'm getting negative 83,634 plus 65,146. And the r-squared value is weak, but it's not nothing. It's somewhat of a weak linear relationship, but there is a relationship. Okay, so number 3 here, use the regression equation to predict the average cost of attendance for a college that is 75% first generation. Put your answer in the yellow cell. So what's interesting here is it's showing that average cost of attendance goes down as the percentage of first generation goes up, which is good because first generation students you would expect to want to attend a less costly college. Okay, so for the prediction here, I'm just going to calculate the y value using this equation. And for x, I'm going to plug in the number that they give me here, 75%. But be a little bit careful because if you look at this axis here, it goes from 0 to 0.9, which means the percentages are in decimal form. So you need to put in 0.75, not 75. Okay? You could tell from looking over here too that these are percentages that are in decimal form. They're all start with 0 point something. Okay, so for my prediction, I'm going to do it in this yellow cell here. You can use a calculator if you want, but I'm going to use Excel. So I'm going to do equals, and then I'm typing the slope here. So negative 83,634 times, and then my x value is 0.75, and then I'm going to do plus, and then the y-intercept here, 65,146, and then I'm going to hit enter. Okay, and that is... Wow, that is a really crazy prediction, actually. That college would cost $2,420. That's way low. But if I look at the trend line over here, like that is actually pretty much... So 0.75 would be up here, and there aren't really any colleges that are that high of a percentage. So that is actually about where it looks like it will be at on the y-axis. Okay, I guess that was... I shouldn't have given you such a high x value. At least it wasn't negative. It could have been negative if I'd gone to 0.85. All right, so that is the answer there. And now I'm going to go to the last sheet, linear regression 2. So this is taken from the same data set. And for each college, this time we have the average cost of attendance and the completion rate in 6 years. So I was curious, if you go to a really expensive college, does it have a higher completion rate? Because people like want to finish as fast as possible, you know, to save money. So I thought maybe it was. So number 1, we're going to make a scatter plot here. So click and drag from A over to B, insert, look for the dots, dots. Okay, so this is a pretty weird looking scatter plot, but there it is. And now we're going to add a trend line. So I'm going to right click directly on the points, add trend line, or you can use chart design and add chart element. Okay, and I'm going to go to the bottom and I'm going to check display equation, display r-squared, and I'm going to move those over here. Okay, so I'm getting scientific notation for the slope right here. So there is a way to change that to be a regular number, or you could just leave it like this. That would also be fine. But if you want to change it to be a regular number, I'm trying to remember how to do this. So I'm going to select the little box around the r-squared and the equation, and then I think there's something in over here. Yeah, okay, so then I'm clicking on the label options, and I'm going to change the category from general to number. And then I need more decimal places here, so I'm going to change this to 3, maybe 8. Yeah, it's a super small number there. Kind of annoying, actually. I will not do this on the real test. This is kind of a pain in the butt. Okay, so you can do it that way. I think there's another way to get it to do that. Let me just double check. So let me undo that. Okay, so if I change the y values maybe to number and then put a bunch of decimals here, does that? Oh no, it's okay. It's still in scientific notation. All right, so I guess your only option is to somehow format this equation box itself. I wonder if, let's see, if I right click on it, yeah, I can do format trendline label, and then I can get to this options over here. Oops. And then it's the one that's under the little bars for label options. Number, and then increase the decimal places until you can actually see what is there. Okay, that's still gonna be a pain in the butt to type in though. All right, let me make this really big. Okay. So now for the prediction, use the regression equation to predict the completion rate in 6 years for a college whose average cost of attendance is $50,000. Put your answer in the yellow cell. Okay. All right, so we're gonna just type in the formula right here. So equals, and then we're gonna do 0.00000666462 times, and then 50,000 is our x value, and then plus, and then the y-intercept here, so 0.296808 6671. Okay, so completion rate prediction is 0.62, and if we look at the trend line over here, for 50,000, oh, it's a little hard to see where the trend line is, hold on. Yep, there we go. Oh, let me make it bigger. Okay, so if we plug in 50,000 on this orange line here, and then look at where the y value would be over here, it does look like it's about 0.6. So this prediction makes sense, 0.629119. All right, so that is it for this practice test. And if you have more questions, you can send me an email or come to office hours. Bye-bye.